Hello, this is Professor Merrill Lichty. In this video we're going to talk about simple linear regression and correlation. First of all, simple linear regression. If we have two variables, we want to know, are the variables related to each other? That's the first thing. The second thing we want to know is what is the nature of the relationship? And finally, if there is a relationship, we want to know if we can use one variable to forecast the other. So here's a few examples to help us understand what's going on here. First of all, we might be interested in the relationship between the daily change in the Dow Jones Industrial Average and the price of Microsoft stock. We might also be interested in the amount of time that somebody spends on a web page and the relationship that has with how much they spend when they go to check out. And another example is if we want to know what the relationship is between the value of a home and the property taxes for the home. This unit is about both correlation analysis and regression analysis. So let's look at correlation analysis. Correlation analysis answers the question whether there's a linear relationship between two variables. And this is done by calculating what's called a correlation coefficient. And this not only tells us whether there's a relationship, it tells us how strong the relationship is. The correlation coefficient ranges from -1 to 1, and the extreme values of -1 and 1 indicate a perfect linear relationship. The notation that we use is rho for the population correlation and R for the sample correlation. Our sample data consists of ordered pairs, so x1, y1, x2, y2, and so forth. And the sample correlation can be calculated using this formula, which is kind of messy and not easy to plug into a calculator. So we're going to let the software handle that for us. Here are some examples of data and relationships that go along with those. Here we have perfect correlation, x and y. You notice all the data points are exactly on that line with no variation from the line. That's pretty unrealistic. This is an example of negative correlation. As x gets bigger, y gets smaller, and the amount of variation is not all that big, which means that the relationship is strong. So we have a negative correlation of 0.95. This is an example of what we call weak correlation. There is a tendency as x gets bigger for y to get bigger as well, but there's a lot of variation, a lot of noise in there. And so we would say our sample correlation is positive 0.32. And finally, we have an example of what you would say is unrelated variables. As x increases, y doesn't have any sort of relationship to that. And the sample correlation is positive, but it's 0.02, which is close enough to 0 that we would probably just go with 0 on that. Here's another example of a very interesting case that we need to consider, and that is when we have a nonlinear relationship. You can see that we have a parabola here, and x and y are very much related to each other, but the sample correlation is 0. And why is that? Well, it's because R, the correlation, is a measure of the strength of a linear relationship or linear association. So if we have a nonlinear relationship, the correlation is not necessarily something that we're going to want to look at. As I mentioned a few slides back, the correlation formula is pretty messy, and we don't want to deal with that. So we're going to let Minitab do the heavy lifting for us here. So on the left, I have a worksheet with two columns, x and y. And in Minitab, I'm going to go to Stat, Basic Statistics, and then Correlation, and put in the variables x and y. The method that we're going to use in this course is called Pearson's correlation. There are other measures for correlation, but we're going to stick with Pearson. And then I want to also select the display p-values down here. Let's look at what the data looks like before we actually run this. You can see that there is a linear relationship here. It appears as x gets bigger, so does y. So we're going to expect that to be a positive correlation. There is some variation about whatever line I would put on that, and when I click OK, I'm going to get this output from Minitab. The sample correlation is 0.776, which is fairly strong, and the p-value that we get back is 0.02. And at this point you should be saying p-value. That sounds familiar. Yes, whenever we do a hypothesis test, we get a p-value back. So what is the hypothesis that's being tested here? Well, the null hypothesis is going to be that there is no relationship, or that the correlation, the population correlation, is 0. And in this case, we get a p-value of 0.024. So at the 5% level, we would reject the null hypothesis that says there is no relationship and go with the alternative, which says there is a relationship. Let's look at regression analysis and see how that relates to correlation analysis. One of the main goals is to determine whether there's a linear relationship between two variables. That's the same as what we did in correlation analysis. But in addition to that, we want to write down an equation that tells us what the relationship is between a dependent variable y and an independent variable x. The simplest mathematical relationship is a straight line, or a linear relationship, and that's why we call this simple linear regression. And we can write that as y is equal to beta 0 plus beta 1 times x. This is the same formula that you learned in high school for the equation of a straight line. Maybe you saw it in the form y equals mx plus b, but it's the same thing. So if we were to think of this as a functional relationship, as a function, we say if you give me x, I can tell you exactly what y is, or in other words, all of the points are going to lie exactly on that line. And the intercept of the line is going to be beta 0. That's where the line crosses the y-axis. And the slope is going to be beta 1. That's just the rise over the run. In the real world, you're going to see relationships more like this. And in this situation, we are going to use what we call a model, which is something that takes into account the underlying relationship, but also allows for there to be variation in the data. And so we have the equation y is equal to beta 0 plus beta 1 times x. And then we add this epsilon, which is called an error term, which really just means the amount of variation that we see above and beyond the straight line. As stated previously, we want to know what the nature of the relationship is between x and y. We can look at the scatter plot and see that there is a relationship, but we want to know what the best fitting line is for this data. Is it this line? Is it this line? Or is it some other line? We want to know which one's best. And in order to do that, we're going to have to get into some math. We're going to use the Greek letters beta 0 and beta 1 for the population intercept and slope. And we're going to use B0 and B1 for the sample estimates for beta 0 and beta 1. So just like we used x bar to estimate mu, we're going to use B1 to estimate beta 1. We have y hat, that's y with a little caret thing over the top of it, looks like a hat. This is going to be what we call the fitted value of y at a value of x that we're interested in. So in other words, you give me a value of x, and based on the estimates for the slope and the intercept, I will give you back y hat. That's just the point on the line. We also have what is called the residual, E sub I. That's just the difference between the observed value y and the fitted value y hat. The I tells us the observation number. And this is just the vertical distance between the line and the actual data point. We have n, that's the number of data points in the sample. So let's look at some actual data. Here we've got pairs of x and y, and the line that goes through this data that I have fitted here is y hat is 7.247 plus 1.787 times x. I won't tell you how we got that line quite yet. But let's look at one of the actual data points. This is the third one. X is 5.18, y is 20.07. And compare that to the fitted line when we take our x value of 5.18, multiply it by 1.787, and add to that 7.247. That gives us a fitted value of 16.5. The residual then is just the vertical distance, or the error that the line has when compared to the actual value, or in other words, how far off is the line from the actual value. In this case, it's going to be 3.57. So you're probably asking where that line came from in the previous slide, and I'm going to tell you now. That line is the line that best fits the data points based on the criteria that we want to minimize the squared residuals. So in other words, we're going to take the summation of all of the error terms squared. So that says take yi minus y hat I, square it, sum it up. This symbol here means sum up over all the data, and find the values of b0 and b1 that give us the smallest value for that summation. So if you remember calculus, then you know that in order to minimize something, we have to take derivatives, set the derivatives equal to 0, and do some solving. I'm not going to go through all the details on how to do that, but the result that we get is the following formula. b1 is going to be the sum of squares for x and y, so SSXY divided by the sum of squares for the x's, and here's the formula for SSXY. Just take the summation of xi minus x bar times yi minus y bar, multiply all those together, or add them all up, and divide that by the same thing but with xi minus x bar. So this gives us b1. In order to get b0, we just take y bar minus b1 times x bar. Now that might seem like it's confusing, and probably it is if this is the first time that you've seen it. Don't worry too much about the details, but if you are interested, you can look into the calculus behind that. So let's look at an example to illustrate what's going on here. We have data taken from the Steamboat Springs Ski Resort in Colorado. We have X, which is the annual income for the visitors in thousands of dollars, and Y is the amount that they spend per day at the ski resort. And this is old data. You can see that people that make $14,000 a year can actually afford to go skiing, which is not the case anymore. Anyway, we have x squared, so that's just this value. 14 squared is 196. We have x times y, that's 14 times 54, 756. And then we have y squared, which is just 54 squared. We do that for all the data points. Do some summing and then averages for the x, the x and the y, and that's going to allow us to make the calculations that we need in order to find out what the regression line is that fits this data. If you look at the data over here, you can see that it looks like there is a linear relationship, and so we want to know what is the line that best fits that data. So let's plug all these numbers in and get the regression line. Let me just note that I don't ever actually expect you to do this on your own. Even with Excel, it can be kind of messy, and the better thing to do is just to use Minitab or some other software. But here's all of the summary information from the previous slide, and we plug all this stuff in. We're going to get our SSX, the SSXY, take the ratio of those things, and we get 3.6397 for the the slope, and 9.6421 for the intercept. And so that gives us this regression line, and that's the one that best fits this data according to the criteria that we have described for what it means to be the best fit. This is what we get when we use Minitab, and you can see that the equation given here is the same. We've got income as our x variable. That means that that's the independent variable, and the way we have this set up with income predicting how much you spend at the ski resort, it makes more sense than going the other way around, although certainly you could have spending be the x variable. But the more income you have, the more money you have to spend when you go on vacation, and that seems to be the better way to set this up. Let's look a little bit more at the regression equation that we just fit. In particular, we want to be able to interpret the slope and the intercept. The slope is going to be just the change in y divided by the change in x. So what does that mean in this situation? We have an estimate of $3.64, and so if we let x change by 1 unit, which is $1,000 in actuality, then we're going to expect the daily spending to increase by the slope, or $3.64. The intercept, on the other hand, which we have here is $9.64, should be the amount that we expect people to spend if they make $0 in income. Now that doesn't really make sense here, because if people have zero income, they won't have any money to spend. And so a better way to think of this is just as a fixed component of spending and does not depend on the income. So let's say we have Kim, who makes $44,000 a year, and she goes to Steamboat. We want to predict how much she's going to spend on a daily basis. So x of p here just means we're going to predict for this value of x, and all we have to do is take 44,000, throw it into our equation, and we have the expected value for Kim's daily expenditures at Steamboat to be about $170 per day. Here's something that you need to be worried about with regression analysis, and it's called extrapolation. So for example, if I wanted to know what daily spending would be for somebody who makes $80,000 a year, could I plug that into my equation and find out what I would predict? Yeah, sure I can. Why not? I've got an equation that says y hat is 9.6 plus 3.6 times x. So I can put any value of x in that I want to. But if you look at the range of the x values, we see the lowest here is about 14,000 and the highest is in the 60,000s. 80,000 is way out here. And so if I want to go outside of the values that the x's have, that's called extrapolation. And it can be very dangerous because we don't know what happens out there. At some point, it doesn't matter how much money you make, there's just not that much to spend it on at Steamboat. And so you would expect maybe that this is going to fall off for people that are extremely rich. If I want to have Minitab do the heavy lifting for me instead of going through all of the calculations in Excel, or heaven forbid with a calculator, I can go to Stat, Regression, Fitted Line Plot, and that's going to give me the graphic that you saw a few slides ago. So it's just a scatter plot with the line that best fits the data. So you're going to specify the response variable, y, that's another name for the dependent variable, and the predictor variable, which is x, or the independent variable, and then just click OK. To get a more complete result, and we will do this a little bit later, go to Stat, Regression, Regression, Fit Regression Model, and you'll see this window pop up. For now, let's just specify the response as our y variable, so dollar spent, our predictor variables as income, and you can see there's a whole bunch of things down here you can do, but for now, don't worry about those. This will give more output that we will look at shortly. This is some of the output that we get from running the linear model. I'll talk more later about all the rest of this stuff, but I wanted to point out that you can see the coefficients are given to us. The intercept term is 9.6. The slope term, or the coefficient for income, is 3.64. And we're given the regression equation down here. Y, that's our dollar spent, is equal to 9.6 plus 3.64 times income. Let's look at a couple more of the measures that we get from a typical regression output. The first one is the standard error of the estimate, or the standard error of the regression line. You can think of this as the standard deviation of the residuals, and basically what it's saying is what's the standard deviation of all the values above and beyond the regression line. So this should be substantially less than the sample standard deviation for the y variable in the case that there is a relationship between x and y. In other words, if x helps us understand what y is, this estimate is going to be a lot smaller than if we just looked at the variation in the y variable. We also have something called the r-squared value, or the coefficient of determination. In this case, we have 94% is the r-squared, and that means that we are able to explain 94% of the variation in the y variable with the x variable. The other 6%, where's that? Well, we're not quite sure. It might be partly due to some other factors, like how many days of a year somebody skis, or how close they live to the resort, and so forth. But at least some of that's going to be due to randomness, and we never will be able to explain the random parts. The correlation, R, the sample correlation, has a relationship to r-squared, and it's not too difficult to imagine why they call these things r and r-squared. If you take the square root of r-squared, then you get r. And if r is positive, that means then that the coefficient on the x variable, or the slope, is going to be positive. So in this case, we have a positive value for B1 that says there's a positive relationship between x and y, so the correlation is going to be positive at about 97%. So that's all I've got for this video. We'll see you in the next one.